Welcome to the final lecture for thermoplastic resins, the Cellulosics lecture. You know how they say last but not least? Surely not. The reason I put cellulosics at the very end is because this has a few interesting points of history and properties that a lot of the other ones don't have. So what we're going to cover is celluloid and cellulose acetate. These are made from renewable resources, specifically cellulose from wood pulp and cotton linter. These are biodegradable and they are sustainable because they come from those renewable resources. The history of cellulosics is not very much like the history of the rest of the thermoplastics. The rest of the thermoplastics I spoke about were purely synthetic materials. Celluloid and cellulose acetate are not. They start off with cellulose from natural products, so cotton linter or wood pulp. Celluloid was first made in 1855 in England by Alexander Parkes, and what he created was cellulose nitrate and camphor, and this made celluloid. This produced a hard, flexible, transparent material. It was patented as a waterproofer, and it was introduced as Parksine, and that was applied to woven fabrics. And this is generally regarded as the birth of the plastics industry. Not the synthetic plastics industry, but the plastics industry. After this point, you also saw a lot of natural rubber products being developed and things like that. So people were taking natural polymers after this point and using them as plastics for consumer goods. It was in the early 1900s where you first saw the first fully synthetic Bakelite, which was actually a thermoset. But this is a thermoplastic, and this is generally regarded as the birth of the plastics industry as we know it in modern times. In 1860s, John Wesley Hyatt acquired, and right now I'm doing finger quotes, he acquired Parkes' patent. What he did was he sort of got his hands on Parkes' English patent and he created a US patent. So this was a little bit of intellectual property theft. But what he was doing with that is to manufacture billiard balls. And he was making a horn-like material with, again, cellulose nitrate and camphor to replace elephant ivory. Prior to 1870, that's how billiard balls were made. They were made from elephant ivory. And he called the material celluloid at this point. This is where we get the term celluloid. And that was introduced in 1872. Celluloid has become the normal term for this type of cellulose nitrate and camphor type of plastic. Celluloid was used as the base for photographic film. Now, if you've ever seen the film *Inglourious Basterds*, celluloid plays a pivotal role because celluloid is highly flammable. And part of the advancement of the cellulosics history was to come up with a non-flammable or reduction in flammability, but still having some of those cellulosic properties. So cellulose acetate was invented in 1904 by George W. Miles. Again, very highly flammable celluloid was good for photographic film. That's why in *Inglourious Basterds* it worked so well as an accelerant. But it was flammable. There were problems with its flammability, so cellulose acetate was developed to avoid that. Miles' work was an extension of other people's work. French chemist Schutzenberger was in 1865, and British chemist Cross and Bevan worked on it in 1894. And what he did, Miles improved the solubility of cellulose acetate in acetone by partial hydrolysis of the cellulose acetate. In 1905, Camille and Henri Dreyfus developed the first commercial process, and then cellulosics were used for lacquer and film production in 1910. This was produced for acetate dope during World War I, for a change, as opposed to World War II, for waterproofing and stiffening the fabric of airplane wings. So World War I was a very interesting conflict. We had both horse and buggy, and we had the introduction of actual air power as an instrument of war. But they were still using fabric as the fuselage of planes, and acetate dope was used on those fabrics. Production was moved from Switzerland to the United States in 1924, and Celanese produced the first cellulose acetate fiber in 1924. Cellulose acetate is also known as rayon, or artificial silk. It has that same sort of silky type of texture. Currently, cellulose acetate is still made by Celanese. It's also made by Eastman Chemical. Eastman Chemical produces both celluloid and cellulose acetate. Now, most people know what Eastman Chemical is, but it's also known as Eastman Kodak. And Kodak is the same one that makes Kodak films. So this is an extension of the same early technology that they still make to this day. When you're talking about the raw materials for cellulose, you're talking about wood pulp and cotton linter. And I'll talk about what cotton linter is in a second. You can vary the reactants, create different derivatives. So cellulose acetate, cellulose acetate butyrate, cellulose propionate, and ethyl cellulose. So cellulose versus starch. Both are natural polymers. Cellulose is the structural polysaccharide that creates the form for trees, plants, other things like that. So that's what it's a structural polysaccharide. And starch, so this is cellulose on the top, this is starch on the bottom. To the untrained eye, they look identical, but they're not. The one difference that gives them their different properties, and starch is considered a globular polysaccharide or a storage polysaccharide. In other words, it gives whoever ingests it energy, whether it be the plant or the person who harvests the potato, but they have significantly different structural forms. And the only reason for this is the difference in the linkage between one monomer unit and the next. This is a 1,4 beta linkage. Here you have I believe a 1,2 alpha linkage, and that's the only difference between them. Monomer is exactly the same. There is higher molecular weight typically in cellulose, but starch can get similar. If you have a low molecular weight cellulose and a high molecular weight starch, they can have very similar molecular weights, but they have very different structural forms and specifically the ability for mammals to digest them. Most mammals can digest starch no problem. Most mammals, with the exception of ruminants like cows, have problems digesting cellulose. And even cows themselves don't actually digest the cellulose. They have bacteria in one of their 4 stomachs that actually digest the cellulose for them, and then that's passed into their intestines. So when it comes to cellulose derivatives, cellulose acetate is the main derivative. This is an acetyl group right here. So instead of hydrogens, you pull this off and you substitute with acetyl groups. This is a link to another cellulose unit and a link to another cellulose unit. This is cellulose acetate butyrate. So as I've mentioned in the past, an R group is a random group. This might be a proton, or it might be an acetyl group, or it might be a butyl group. This is the butyrate group right here. Cellulose propionate uses a propionate group. That's what's found here. So these R groups may be a propionate group or they may be a hydrogen. And in the case of ethyl cellulose, these R groups may be a proton or, in other words, a hydrogen, or an ethyl group shown here. So instead of these groups that contain a carbonyl group, this just has an ethyl group attached to it. Where do you get your sources to make cellulose? Like I said, this comes from a renewable resource. What are they? Trees and cotton. So this is made from wood pulp. So there's wood chips and there's wood fiber. Fiber is the end product from pulping. So you take your wood chips, you pulp it, you you put it in with a lot of chemicals to pulp it, and fiber is the end product. If you keep working on it, you get fiber. So the pulp, an intermediate product, is what the cellulose comes from. Or it comes from cotton linter. So once again, cotton is an agricultural product. It is a plant. So you have the cotton fluff, the lint itself, then you have the cotton seeds, and the linter is what cellulosic fibers immediately surround the seed itself. Not the lint, but the linter. And this is often used for making cellulose fibers for cellulose acetate. It's also used for making gunpowder, and it's also used for making paint additives. So here's the cellulose acetate synthesis. The most stringent synthesis I will hold you to is the synthetic procedure on the very bottom. This is how it's made. You have cellulose in an ice bath with acetic anhydride and sulfuric acid, and then this creates these acetate groups here. It is partially hydrolyzed to hydrolyze these sulfonate groups back to hydroxyl groups, and that's your cellulose acetate. So there, for all you chemistry nerds in the crowd, that's the actual chemical synthesis. For all of you who would rather die than learn any chemistry, this is essentially the reaction that I will hold you to. But it creates a acetyl functionalized surface of a cellulose fiber with acetic acid as a byproduct. The most common form of the acetate has a substitution to 2 of the 3 hydroxyls to acetate. So in other words, there's acetate here, there's acetate here, and then one of these hydroxyls remains as a hydroxyl. When it's fiber grade, it's dissolved in acetone to create a viscous resin, and then that's extruded through spinnerets to get your fibers, your rayon.